Welcome to YMT215 Logic Circuits. Today we'll speak about the first part of Chapter 1, Introductory Concepts. We will try to cover only two main topics: digital and analog quantities and binary digits, the logic levels, and digital waveforms. So when we say digital and analog, what comes to our mind? So in brief, before I explain about these two, in brief, we have electronic systems that we use on daily basis. Think about your phone, think about your computer, think about tablet, or whatever you are using that has some electric or electronic circuitry in it. So that is a circuit. 99% would involve digital components and maybe some analog components. So that's why we have these two components, and we'll explain what they are. Analog, when we speak about analog, we speak about continuous quantities that do not have a discrete nature. They are attached to one another, like one wave or one continuous line. Now this line may be a curve. It's not necessarily to be a straight. It would be a curve, or it depends on how it is distributed or printed or how it is displayed. But it is continuous. It's not discrete. The quantities are attached. So you may picture this thing in your mind. The second concept or part of circuitries we call digital. So we speak about discrete quantities that do not have continuity in them. They are not attached. So now we speak about these two in distinguished sense. One of them is continuous, analog, and the other one is discrete, separated somehow. There are gaps in between. Okay, when we speak about our reality, our nature, the way we speak, our voice, the vision, these are analog quantities. And most of our daily quantities, or the quantities that we have in our daily life, or things that we touch and use, are actually analog or composed of analog things. However, the revolution in our industry is based on digital quantities. And for that reason, we have to have some relationship between these two. Now think about, in order for us actually to distinguish between these two in a real example, think about the temperature for a whole day, okay? Or maybe over 12 hours like here. Now if we calculate the temperature, now this is in Fahrenheit, it doesn't matter. Whatever it is, it doesn't matter. But you think about it as just a measure of the temperature, you know how to convert between Celsius and Fahrenheit. It's just a metric for temperature. So we have a continuous waveform over 12 hours, not actually, this is 24 hours, I'm very sorry, because 12 and 12 here, AM and PM. So we have for 24 hours here, my eyes went to 12 here, I didn't pay attention. So let's say for a whole day, okay? For a whole day, certain day, we have a measure, or we have a signal for the temperature drawn this way based on different values the whole day. So this is a continuous signal. It's an analog signal. Think about distance. If you are just driving a car or riding a bike, if you check the distance of whatever your journey, it will be also continuous, analog. How about the sound? Now, as I'm speaking now, we have a sound signal. If we continuously measuring it, we will have also an analog signal. But how can we simplify the signal? And why do we need, actually, before we simplify it, do we really need to simplify this one? Yes. Why do we need to simplify the signal? For a few reasons. One of them is, let me just explain to you this simple fact. This is a continuous signal, so we have an infinite number of values. So we have a value here, a value here, so many of them, infinite, and dealing with all of those at once is not easy. How many values are we going to deal with? But for some reason, if we take quantities, like let's say at each hour, we take just sample of the temperature. So we have a sample here, a sample here, a sample here, like this photo, like this image here. In that case, we have a limited, okay, or finite number of values. So dealing with finite number of values is for sure easier than dealing with infinite. So this is an infinite number of, this has, sorry, an infinite number of values, okay? So this is the beginning of the concept of digital or discrete values in this case. We have an analog signal, we take some sample of it, or samples. Here we have samples over a certain period. Usually we take a fixed time sample, so over 1 hour. So 1 hour, next hour, and so on. So we have a set of values, discrete values, and we can calculate their amplitude or their values here. Why temperatures? Temperature has its own measure, so we know what it is here, what it is here, and so on. So here we need to deal with only 24 instead of maybe millions, maybe billions. It's continuous. We don't know exactly how many of them are available, so it's just infinite. All right. So the concept of taking samples here is called actually quantization. We take quantities, okay? So this is called quantization. And so we have these values. If we transfer these values to a digital value, and we will speak about it, a code. So here, let's say 75 here, it's a bit less, just an example. Let's say 75, if I transfer it to its representation in binary, and I'll speak about it in a while, then what are we going to have? We will have just a code. So we have digitization in this case. So we take values, we digitize them, then what's the point? I transferred unlimited number of values to limited number of values, then I coded these values, and based on that I can store them as codes in my computer, ones and zeros, and I'll explain about ones and zeros in a while. Okay, so why should we do that? Why should we even bother doing this? For a few main reasons. The first one is, as I said earlier, for continuous signals we have an infinite number of values, and that's a problem. Dealing with always so many values is a troublesome. Is a trouble. So it's not easy for you to deal with all these values. The second thing, digital signals or digital values or digital codes are usually more reliable. Why? Because we have only two levels, 0 and 1. I will explain about them now, or low and high. And those, actually, the error in these two is much less than in so many values. Here we have so many values. So we expect any value between 0 or whatever here. Okay? Plus, look, so many values, again, unlimited. I compare it to a limited value. How about storage? So we need much less storage, and that's also an advantage. So that's why we have a more robust signal. It does not actually create more errors, or sorry, it does not get actually much bothered by transferring on the transmission line. It's more robust. It's also less susceptible to noise. The noise doesn't disturb it much, and we will speak about it in a while also. And it needs less memory. Usually I ask such questions on the exam, like maybe compare, like creating a comparison between digital and analog, and why we need, let's say, digital signals over the analog signals that we already have. All right, so what kind of systems use digital components, or do we even need to have digital components in electronic systems? I said earlier yes, because most of actually the technology that we have nowadays rely on digital components or digital circuitry. However, we have a fully analog systems fully deployed analog components in analog systems. There are some, and we have also full digital circuitries as well. Let's take some examples. Let's just speak about few of these examples. I think you guys are very familiar with the public address system. Think about this. When we speak like with our own human voice and we would like to enlarge it, amplify it. So this is a system where we speak by our voice. So we have originally the input to our system is actually sound waves. So these sound waves are picked up by a microphone. Why do we need to have a microphone here? It transfers or converts these sound waves to another form, audio signal. And this audio signal is a change actually of voltage versus time. So it's a signal like this, voltage versus time, instead of just the vibration of the voice signal. And when we have this voltage signal, we can apply an amplification to it. So we amplify it. So amplification in this case is like enlarging it, multiplying it by certain value. So it's the same signal here. However, it's bigger in amplitude. And then we need to reconvert this signal to voice again. Why? Because this is just a voltage signal. For us human beings, we can't hear it. We need another form, which is the sound wave. We transfer it back to its original state, but in a bigger value or higher amplitude or larger amplitude. So here we don't have any digital component, although nowadays this amplification process is done based on a digital process or a digital digital amplifier. However, it's not needed. It's totally analog. All these components are analog. Do you need to know the nature of the amplifier? You don't have to. This is not your area of study. In this course, we don't have to discuss anything related to amplifiers. It's totally related to electronic courses and similar relevant departments. So you don't have to worry about it. But this is an analog system. It receives an analog signal, converts it, amplifies it, then converts it back again to the original nature. How about another example where we have digital components involved in the whole process? Think about the compact disc, the CD, or think about the DVD, or whatever you are using in your computer now. Basically, we store digital data on compact discs. Digital data means here in this case ones and zeros, and in a while we will reach to them. So we just have two components, in this case ones and zeros. There is a certain mechanism for storing data on a compact disk, and I believe you studied this in Introduction to Computer Science. So it is basically burned on the CD by a certain mechanism. We have like a pattern for one and zero. Like there is pulse, there is no burned in certain process or in certain way. So in order for us to pick them up, we can use a laser diode, an LD, an optical device or an optical sensor that senses the nature of 1 and 0 on the CD, on the track. And that's a digital nature. So we receive these. They represent certain data, but we don't know. It's just a series of ones and zeros, so we need to convert them to their nature. We use digital to analog converter, DAC. So we have a digital signal stored. What we need to do is we need to convert it to its nature, so we need to use digital to analog converter. And this digital to analog converter will regenerate the original signal coming to the CD or the DVD before digitizing, before the digitization. So it's most likely electric signal, an electric signal. So we will get an electric signal, and then this electric signal will be converted to its own nature. Maybe music, maybe video, whatever, maybe an audio or video or whatever, maybe an image. That's something our eye or ear or our senses will receive it, or actually understand it, comprehend it. Okay. This is the whole process. We have the CD, and we need the driver of the CD, and this CD driver will just make the CD rotate so that we receive or we reach all the tracks based on whatever we are accessing. We have the data stored on these tracks here. Data is actually composed of ones and zeros, like this, a train of ones and zeros. We don't know what they are until they are converted to their own nature. So the nature could be, as I said, could be of any type, not necessarily audio or video. It could be an image that we see. It could be also a print. If you are printing something from a CD, it would be transferred to written text on paper pages, and so on. Maybe it could be a file that you open and see by your eyes. Okay, this is another example. Also, writing on the CD itself requires conversion from an analog signal, it could be electric or of any other form, to digital. Then we can write it on the CD. Okay. So we spoke a lot about digital signals, and we said that they are actually composed of two states only, 1 and 0. All right. So what's the system and how can we deal with it? Now I want you to go gradually with me in this class to understand the concept of digital signals. Imagine we have two levels. One of them is lower than the other. So we have two levels. One of them is lower than the other. We call the lower one, we call it low, and the higher one, we call it high. So we have two levels, only two states, two levels. And we code whatever we have as a value based on these two states. So high and the low, nothing else. And the high we represent it by 1, and the low we represent it by 0. And what we refer to 0 and 1 in this case, the two-state number, we refer to it by binary digit or a bit, binary digit. So binary digit, it could be a 0, it could be a 1, or it could be a low state or a high state. So only two levels. We represent whatever we have based on these two states only, nothing else. Now, this is the idea. We can code anything, any quantity that we have into series of ones and zeros, or series of high and low states based on binary system, or the binary digit that we have, or the bit. All right, so that's the idea. And what we are going to use in this course is exactly what we call it, the positive logic. The positive logic is considering the high as 1 and low as 0. We have the negative logic considering actually the high as 0 and low as 1. We are not going to use this one, just for your info. This is the negative, is the other way around. High is considered 0 and low is considered 1. No, for our course we will consider the positive 1, high is 1 and low is 0. Okay, I'm sorry. So how can we compose digital signals based on what? So how do we know that this is within the high and the other one is within the low? Or how can we know a certain value is within low, not high, or within high, not low? So we need to have a mechanism to understand. In basic sense, you don't have to worry about here, I'll explain it on the figure. Imagine that we set a rule like a low state can go from minimum to maximum, and the high state can go from minimum to maximum. And these minimum to maximum we refer to voltages. Why? Because here we deal with actually electric pulses. Okay, so we deal with electric pulses and we convert them to what? Ones and zeros, or high and low. So in that case, we need to have a sense of a signal. The sense of the signal here is voltage. You guys are familiar with the voltage, you studied it in physics. All right, so we have two levels. most likely we will have this one starting from 0, okay? And we have like those vary based on the type of electronic device that we use. For example, we have a very common electronic device or fabrication called CMOS, complementary metal oxide semiconductor. You don't have to worry about it. You're not supposed to understand all the details of it. We will explain about it if it comes with us. However, it considers the high state range, the high state here that we have, the binary one, range. So the high state here range from minimum to maximum between 2 and 3, 3.3 inclusive. So here 2, 3.3. Whatever between, including the edges, is considered high. While from 0 to 0.8 volt is considered low. How about in between? Between higher than 8, lower than 2. So 0.9, 1, 1.23, etc., whatever between these two is called unacceptable. Sometimes we call it fuzzy. So we are not quite sure what it is and we do not accept it. It could be 1, it could be 0, so it's not acceptable. The level here should be from 0 to 8. If it is higher than 8, it should be in this range between 2 and 3.3. So I may ask such a question like, I give you these maximum and minimum, I give you the values. Let's say I give the photo here with like, let's say 5 here, 2.7, here maybe 1.5, here 0. And I give you a value, I tell you, let's say 1.1. Is it within the low or high? So you need to check these borders and see exactly where the value is and answer. In this case, you need to check between 0 and 0.8, whatever in between is low. Higher than 0.8, lower than 2 is unacceptable. And between 2 and 3.3 is high or binary 1. Okay. So binary 1, binary 0, or 1 and 0 in brief, they compose some series of pulses, 1, 0, 1, 1, maybe 0, 0, 1, 1, 1, etc. This is what we call digital waveform. A waveform is composed or created or generated from the change of pulses states. So we have high, low, low, high, high, etc. So we have a train of pulses, multiple pulses. This is what we refer to by digital waveform. Now, if the transformation from high to low, this is what we call positive going. So we go from high to low, okay? I'm sorry, from low to high. I'm very sorry, the positive is going actually from low to high. So we rise, this is what we call the rising edge. The state goes from low to high, and in that case, we're going positively, actually positive going. And this is exactly what we refer to by positive going pulse. We go from low to high, then we have rising edge. After the high state is finished, we have a falling edge. Remember those, why? Because we will need to use them in the last few chapters, okay? This is the T0, rising edge beginning, and T1 is the falling edge beginning, okay? We have the negative going. Negative going is going from high to low. So we have the falling edge. The falling edge was at the end, previously in the positive. Now with the negative, it's starting from T0. This is the falling edge. We change from high to low, and then we have the rising edge, back again to high. So all you need to know is like two different types, going from high to low, or going from low to high. And you need to know what the falling edge is representing, what the rising edge is representing. So the falling edge is actually going from high to low, and the rising edge is going from low to high. Now depending on, okay? Before I go to this slide. Now this is what we call ideal waveform, or ideal actually representation of a digital signal. Ideal means actually something that we don't have in reality. Why? We cannot actually achieve exactly 100% like angles like this, extremely perfect shaped rectangle. In that case, what do we have in reality? We have something like this. In reality, we have a bit of a messed up actually signal, where we have like ripple somewhere here, overshoot. This is one type of ripple. You don't have to worry about it and why it is generated. Actually, it is generated from the imperfection of the electric signal, or the electronic circuit used to produce this pulse. Okay, we have also ringing due to the capacitance and inductance in the signal, also the droop. So it is just referred to like unwanted actually ripple or unwanted imperfection in the signal. So look, we have inclination in the falling edge. We have inclination also in the this is the rising edge, and also in the falling edge. So how can we calculate the pulse, or what kind of pulse here is considered? We don't consider all this one as a pulse. We take only from 10% to 90%. So we consider this area only as a rise time. So this one is the part that we wait for the signal to reach the 90%, and the same goes here. When it drops between 90 and 10%, we have the fall time. So we take exactly whatever in between here as a pulse width for our signal. Okay, so here we don't have, it's zero. The fall time is coming exactly at once. Here, no, it's coming between 10 and 90% of the signal, and here as well. In order for us to cut this ripple or imperfection of the signal, we use until 90%, we don't go up, and also we skip below 10% because we have some ringing here or ripple. Okay, so in that case we have the pulse width calculated based on 50% of this signal, and we ignore whatever below 10% and 90%. Do you need to know all these details? You don't have to. I'm just explaining to you for your own knowledge. Why? Because you may need it one day if you see it, and like if you are designing your own oscillator or so on, whatever generates these pulses, you need to know that this is the real pulse, not this one. This is an ideal one. Okay. So I said about the ringing overshoot is actually produced by the imperfection of the electronic circuit. So we have an inductive and capacitive. They produce some either ringing or overshoot. Also the droop is produced by the problems attached to capacitive, like we have some certain stray capacitive in our circuit due to certain fabrication, or due to some components, imperfect components in the circuit. All right, so I explained about the rise time, I explained about the fall time, the time needed for the signal to go from low to high state, the time needed for the signal to go from high state to low state, or high level to low level. We explained about the 10% to 90%, so I don't want to explain about them again. Do I ask questions about such thing? Not likely. You just need to know it for your own knowledge and personal knowledge. But however, here, this is important. I mean the 50%, and we will speak about those later on, not now, in the design of pulse generators or maybe counters later on, not now. All right, let's go to another topic, or another part, sorry. Now, we have a pulse train, multiple ones and zeros, and we are not quite sure actually when the one will come and where the zeros come. Do not look at this. This is like perfectly arranged, 1 0 1 0 1 0, etc. However, we need to explain about one concept that we have in these trains, or the pulse train here. We have two main types. One of them is what we call periodic. Periodic means what? Look at the signal from here, from this point to this point. Okay, we have high state, or 1 0, then again after this one, after this point, we have 1 0, which is actually the repetition of this one. So we have this one repeated. So if we copy this from this point, copy this part from this point to this point and drag it to here, we will have a perfect match. And this is what we call periodic signal, a signal that repeats itself after a certain period. So we have a period. Once this period is done, then we have again another signal, which is perfectly matching the first one. After this period, again, the same copy, again, the same copy. This is what we call periodic signal. We have a fixed period. We don't have T1, T2, T3. They are all equal to one period T, okay? And in order for us to calculate what we call frequency, usually we don't deal with time in all cases. We deal with frequency. Frequency is exactly the reciprocal of the time. So if we divide 1 over time t, that will give us the frequency of a periodic signal. Okay, we have a non-periodic signal. Non-periodic, we don't have exactly a repetitive signal after a certain period. You see here starts by 1, then it goes 0 for a certain time, then we have a bigger 1 state, like a number of ones, then etc. So we don't have a period here. We don't have a frequency, a fixed frequency for the signal. Why? Because we don't have a period for it. That's why such a representation usually is not of our interest in having a synchronization clock, and I will explain what clock is in just a few slides. You don't have to worry about it for the time being. Just hold on a little bit. So we have a periodic signal, a signal that repeats itself after a certain period. We can have that period and take the reciprocal to get the frequency. For the non-periodic, we don't have a fixed period, and we can't calculate a real frequency of it in this case. Okay. For periodic signals, we can calculate what we call the duty cycle, and it's extremely important for, further chapters. We will need it for a design. It's a factor that needs for different designs of oscillators and counters, etc. So duty cycle is exactly like this. Let me explain to you here. Look at this. This state, which is high, we call it on state, and the low one we call it off state. Okay, look, this is high, this part is high, this part is low, here, this one, this part here. So this is a period, the whole period. If we calculate, find the on state and divide it over all period of the signal, then we are having what we call duty cycle, but after multiplying it by 100 to get it in terms of percentage. So on state over all periods. So we have pulse width here. Pulse width, on state pulse width, or on state time. On state time here, TW. It's extremely important. And we have the period. If we divide the time here between this edge and this edge over T1, or actually T in this case because it's fixed, and multiply it by 100, then we get the duty cycle. So remember, the pulse width for on time is referred to by TW, and that gets us a duty cycle. Do I ask about these things? Sure. This is an example, and this is an easy example actually. Look at this. These are numerical values. We have between 0 and 1 in milliseconds time. We have an on state. So what is the pulse width of this on state? 1 minus 0, that's the pulse width, that's 1. Okay, how about the period? Now look at the period. Why do I say period? It's a periodic signal, okay? Portion of periodic signal. So what's requested? We need the period, we need the frequency, we need the duty cycle. Now look at the period. We start from here. We move high state, then we come back to low state again until we go back to rising edge. So from here, from 0 to 10, we have the period. So 0 to 10, that means the period is 10. 10 minus 0, that's 10. Okay, we got the first one. How about frequency? Frequency is the reciprocal of the period, 1 over 10 millisecond. That is actually 100 kilohertz. You can divide it and pay attention to the units here, milli. So you need to convert it to second, multiply it by 10 to minus 3, and that will get you the frequency in hertz, or if you want in kilohertz, and so on. Okay. How about the duty cycle? The duty cycle on state over the whole period. So what is the duration of the on state? 1 minus 0, that's 1. How about the whole period? That's 10. So 1 over 10, 1 millisecond over 10 millisecond multiplied by 100. So that's exactly how we calculate it. So the duration divided by the whole pulse period, okay? And that will get you the duty cycle. The duty cycle in this case, it's 1 over 10, that's 10%. So the on state is only 10% of the signal. That's how we understand it, okay? This is another exercise for you. Try to do it. Actually, it's very similar. We have the period and we have the on time. So you need to determine the frequency, the reciprocal of this, 1 over this. And we need to get the duty cycle, 25 seconds, milliseconds, or 150 milliseconds multiplied by 100. You can get the duty cycle. All right. So we explain about the duty cycle and relevant issues to the waveform. Then how about the pulse time, and how about what actually synchronizes the pulses that we have? How can we know that this is periodic? How can we know that the pulse, one state, high state and low state, are generated in a fixed time? So I said earlier, I will speak about something we call it clock. Clock is an oscillator used for synchronizing the whole process of generating digital signals or digital pulses. So the ones and zeros, let me show you like here, those are generated based on synchronization process. So we have a synchronization process that allows us to generate these pulses on a fixed time. So we don't have an odd nature of the bit time. The bit time change of 1 to 0 and 0 to 1, etc. These are generated based on a synchronized nature with a clock. It is like, clock is like, imagine it is like a manager says, okay, start the process now, end the process now. Start, end, start, end. It's like an organizer of the beginning and the end of the processes of forming of binary digits or bits, okay? So now look, this is a clock. The clock is like a train of 10, 10, 10, etc. So this is the bit time. A change from 0 back again to, from 1 back again to 1. This is actually a period. It's a periodic signal, of course, the clock. So this is the bit time. Based on this bit time, we compose 1 or 0. So again, in order for you to compose 0, it should be the same period of this 1. Why? If we have this one in like shorter period, we will have, ultimately we will have some synchronization problem. The 0 is longer than 1, so they don't have the perfect fit in the representation. So one state should be equal to 0 state as individual bits. Why? Because we may have combination 2 or 3 or whatever, 2 zeros after each other, 2 ones or 3 ones after each other, or whatever. But still, this composition here, this value or this period should be exactly the clock period or the clock time, the bit time of the clock, okay? So this is actually a counter. You don't have to worry how we designed it now. We will study it later on, but look at the clock. We have a synchronization for the waveform A, B, C. For A, we have 1 bit time for forming this bit, and then we have like a longer period, 1, 1, 0, 0, etc. So those, you can see this timing diagram, these dashed lines show you the bits composed. So here we have 3 zeros. It's exactly, if you count like 0, 0, 0, 0 for C, 0 for B, 0 for A, 0, 0, 1, it's a counter, 0, 1, 0, I don't have to explain it to you now because we will study this one later on, but this is exactly the formation. So we have 1 bit time or 1 period of the clock. We generate the bits based on it. The next bit also based on it. The next bit and so on. So this is the synchronization nature. We have a manager, which is the clock, tells us, okay, this state is finished, compose another state. It doesn't matter 1 or 0. That refers to your own design. Later on, we will learn how to design these logic circuits. All right. Now we have a series of 1s and 0s, or digital signals, or digital actually data or codes. Sometimes we refer to. Let's say we have them on a memory of a device, or maybe our computer, or maybe phone. How can we transfer them? If we want to transfer them from one point to another, we need the mechanism for that. We need a transmission line or a transmission mechanism or medium. So we have two main ways. The first one is sending these bits serially on one bus. So there will be a train. Like we have one passage and we ask people to come one after another from that passage. Okay? Just one passage. Maybe it's enough for only one person, one bit at a time. So we ask them to come like a queue after each other. It will take actually time to finish all these bits. Why? Because we go one after another until we pass all the bits. This is what we call serial. So we need only one bus to take all the bits from one point to another, and they will go serially one after another. Okay? We have the other mechanism, parallel mechanism. So in that case, we need multiple connectives in one master bus. So this is a master bus that has like 8 cables or 8 connectors in it, and we transfer the bits from the sending device or the sending point to the receiving point at once. So all of them will be transferred by the speed of transferring only one bit of this. Why? Because they are transferred at once. So we need just one synchronization, a clock, to transfer them from one point to another. Now, the advantages and disadvantages, and I usually ask about these questions. What do you think about the advantages and disadvantages? This one, let's think about it from this perspective. This one is slow. Why? It takes time, because the bits will go after each other. This one is faster. Sure, because it takes only the time of one bit to transfer all the data. This one is more expensive. We need separate connectors. If the number of bits, the width of bits, not only 8, if 16 or 32, then the more expensive the connector or the bus will be. And this one is just one bus that takes the data from one point to another. This is a way to compare. Okay, so it takes longer time, it takes shorter time, it's more costly, it's cheaper for sure. Okay, so this is the idea. Let's think about an example. Determine the total time required to serially transfer the 8 bits contained in the waveform A here. We have 8 bits here. 8 bits means what? 1, 2, 3, 4, 5, 6, 7, 8. You see, this is what we call synchronization diagram. This is the clock. We start from here, from the beginning of the clock, and we carry on until the end of the clock. Okay? So we need to calculate the time of transferring all these bits serially, okay? And we need the final representation. If the clock cycle or the clock frequency is 1 megahertz. So the frequency is given, we know that it is 1 megahertz, then we can convert it to time. What's the time? Time is the reciprocal of frequency, so 1 over 1 megahertz, that is exactly 1 microsecond. Why megahertz? In this case, 1 divided by 1 megahertz, it will be 1 to multiplied by 10 to 6 minus 6, sorry, and that is exactly microsecond after all. So we have for each bit, in order for us to transfer 1 bit, we need 1 clock cycle, and the clock cycle time is 1 microsecond. So for transferring 8 bits, we need 8 clock cycles. You can count them, 1, 2, 3, 4, 5, 6, 7, 8. But each bit needs 1 clock cycle, so 8 bits need 8 clock cycles. So we need 8 times 1 microsecond, so we need 8 microseconds to transfer all the bits. And the bits will come out exactly in this form just by shifting. So this will be the least significant, the most significant, or whatever you refer to them based on your own design. You don't have to worry about what's least significant, what's most significant. We will explain about them later on in our next chapters. So this is the idea. Again, you calculate the time of the clock each bit needs for transferring it from one point to another. It needs 1 clock cycle. The clock cycle is the reciprocal of the frequency. Multiply that by the number of bits to be transferred or the number of clock cycle needed. So in that case, it's 8 microsecond. Why? Because we have 1 microsecond for each clock cycle. We need 8 clock cycles to transfer all bits. And that's the final representation, exactly like here. Take another exercise. If a binary data are transferred on a USB at rate of 480 million bits per second, so Mbps, 480 Mbps, how long it will take to serially transfer 16 bits. So now we know, what we know here is we have the rate, okay? So the rate is 480 Mbps, and we need to know how long it takes to transfer 16. So this 480 megabit are transferred in 1 second. So 16 bits will be transferred in how many seconds? So you can calculate it. This is the end of this session. I'll create another session for the first chapter, second part. Till then, have a good time. Goodbye.